Next up, I apologize already, but I think it's Wojciech Kozlowski. Is that correct?
Wojciech Kozlowski.
Okay. And he's going to be talking about quantum internet and what they are doing in the IETF, so the Internet Standards Organization, on the topic. And of course, general primer, quick primer also on the topic.
Okay, yeah, thanks for the introduction, and hi everybody. My name is Wojciech Kozlowski. I work for SURF, which is the Dutch IT cooperative, and amongst other things, they are the National Research and Education Network in the Netherlands. But I'm going to talk about the quantum internet. I am also the co-chair of the Quantum Internet Research Group at the IRTF, and I'll mention that as well. So first, to understand what the quantum internet is, I'm going to do a little crash course on quantum physics, just about enough to understand what it is so you can relate it to practical applications later, hopefully. So to dive into it, I'm going to explain a concept called quantum entanglement. Imagine you have two parties, Alice and Bob. Alice and Bob both have a qubit each. Think of qubits simply as the quantum equivalent of a bit. It can be 0, 1, or something in between. We're not going to go into detail of how that works. If those of you who are familiar with Schrödinger's cat. Now, quantum entanglement is something that connects these qubits. So these two qubits are connected at the physical level and across over a distance. So for now, let's just take it as it is. There's some kind of physical level connection between them. Now, both sides will now try to read out their qubit as in extract what bit value their qubit is storing. So they do that. And both sides, Alice and Bob, find that they get the result 1. That's fine. It's random. If you flip 2 coins, you're also likely to get a 1, 1 on each side. They prepare another set of entangled qubits, and they do the same kind of experiment to read out the value of their qubit. They get 0, or tails in the case of a coin. Again, can happen. These are coins. They're random. They do it again. One more time. They prepare entanglement. The qubits are entangled, and they try to read it out, and they get 1 again. And they keep doing this again and again and again and again. And if the quantum entanglement is prepared correctly, perfectly, this will always keep happening. And that's essentially the gist of quantum entanglement at its core. Basically, when you have a pair of entangled particles, wherever they are, they will always yield a random outcome. So the outcome was random, but it was always correlated. I use the example of them always being the same, but always opposite is also possible. I'll stick to always the same for the rest of the slide and the presentation. The non-quantum classical, as quantum physicists call it, equivalent analogy would be if you were to specifically flip 2 coins in 2 separate locations, but somehow every single time you flip these 2 coins, they always land on the same side. You intuitively know that this is not possible without if you just flip 2 independent coins, but with quantum mechanics and quantum entanglement, you can achieve that. Some interesting things that will also become useful is that this is a random outcome. So it's important that this outcome is random. It was prior to the measurement, prior to the readout, it was undefined, not unknown. And this is very important because this provides a layer of security, because it's not something that you can somehow extract before that. Before the readout, then their number did not exist. And it's a bit of a quirk of quantum mechanics. And the way one would represent it, I guess, semi-mathematically, was something like this, is that in this entangled state, what you have is your 2 qubits are either in a tails, so 1-1 state, or in a heads, 0-0 state. Okay, that's great. How can we use it? Well, one example would be what's an application called quantum key distribution. So imagine there's an eavesdropper now. Somebody tries to tap the connection. What happens then to your thought experiment? Well, if you have entanglement and you try to measure it, well, now you're going to start getting mismatches. there's an eavesdropper. The presence of an eavesdropper will affect the entanglement to the extent where your results no longer match. So they prepare it again, and again it doesn't match. They prepare it again. It can match sometimes, but that's no longer guaranteed. So my point is that anybody else trying to tap into the connection will inevitably perturb the system. There is no physical way to not perturb the system in a way that is not observable. It's just, this is a property of quantum mechanics that is used for secure communication, can be used for secure communication. So what can Alice and Bob, what can the two sides do to use this fact? Well, they just take a small subset of their outcomes, they compare it with each other, and if all the compared outcomes match, they don't have an eavesdropper. If some outcomes do not match, they have an eavesdropper. And if you do it enough times, you can do the statistics and you can get some good degree of confidence that you indeed do not have an eavesdropper on your channel. And this is effectively the gist of quantum key distribution. There is almost nothing more to it. The more to it is that if you have noisy systems, which is everything in reality, then you have to do a bit of extra maths on top of all of these things to distinguish between noise and eavesdropper. But it is possible, and people are building systems with it. This is all doable. So that's quantum key distribution. The quantum key distribution is an example that's already being implemented, and it's already possible. I'll talk about that again in a moment. Now I'm going to talk a bit about slightly more futuristic things, what else you can do with quantum entanglement once it comes along. For example, teleportation. Sounds cool, so let me go through what it means in terms of quantum context. If you have a sender and a receiver, and the sender and receiver again share this entangled qubits, and let's say the sender has some other piece of quantum data that they want to send to the receiver, how do they do it? There's some things I haven't said yet, but for example, or maybe you know already, but it is not possible to copy quantum data. So therefore, if you were to send this quantum data down a fiber or in some other channel and you lost it, well, you couldn't have made a copy to retransmit. That's not possible with quantum mechanics. But if you have entanglement, what you can do is you entangle your data with your qubit on the sender side. You perform a measurement, so therefore destroying the entanglement. And since you measure 2 qubits, you have 2 bits of information. Each of them yielded a random outcome. You send these 2 bits to the receiver, and from these 2 bits, the receiver can actually reconstruct your original piece of quantum data. And so therefore, you've teleported data from the sender to the receiver. So in short, quantum entanglement also allows you to transmit quantum data. So it allows you to tell by teleportation. It destroys the sender's copy of the data. It's not copied, it is destroyed at the source. And it has consumed the quantum entanglement, so you cannot use the same entanglement channel repeatedly. You have to keep recreating the entanglement to do it again and again. The quantum data never actually entered the network itself. That's a very interesting little piece of information. And so therefore, all you need to do, or the entire network, the networking aspect of it, is that you need to keep creating this entanglement between the sender and receiver in order to keep allowing for teleportation. So that's another example of what you can do with quantum. And kind of super far future, what you might be able to eventually do, actually say super far future. SURF got awarded will be hosting a quantum computer in 2026, so hopefully not so far future. But if you have a server, and you want to connect to that server, and you have a client device, and you want to execute a computation on that computer, you can actually, with quantum mechanics, execute it in a way where the server does not know your inputs, does not know what computation you performed on it, or does not know the outputs of the computation. All of it is blind. It's blind to all of that. How it's achieved with entanglement is that you perform you have, again, entangled qubits. Entanglement is really important. You perform a measurement with some random parameters on your side of the entanglement. That yields a random outcome, but that random outcome is both random on the client and the server. But from your output, the client's output, you know what state the server is in, but the server does not know. And that's important, because you use this information, the fact that the server does not know what state its qubit is in, to send it encoded instructions to manipulate that qubit, perform computations on its side, and then send you the output. And then from that output, you decode your actual result. And that's blind quantum computation, how you've hidden your inputs, outputs, and the actual computation from the server. So in summary, as I said, the client performs measurements. There's some random element to it, which is part of the protocol to hide this information and then later to encode the instructions. And the key thing here is that the entanglement allows the client to prepare a state on the server, which the client knows, but the server does not. And then there's encoded instructions being sent to the server, and then the answer, therefore, is also encoded when it's sent back. So what I want to highlight is if we're going to be building quantum networks, our key abstraction, our key building block is not actually the transmission of quantum data, but it's entanglement. And that's kind of what if you're going to take away one thing away from today, that's what I'd like you to take away, is that if we want to build a quantum network, we want it to distribute entanglement. And that's the kind of the long-term future. Some extra pieces of information about quantum entanglement that are useful to take away is that there's no theoretical limit to the distance over which it can survive, which makes it a very good tool for networking, provided you can actually create it over a long distance. If you can create over a long distance, in principle, it can stay like that forever. And maybe in the future even to different planets, or at least over space. And another key thing to take away from this is like why entanglement and not data transmission is because, as you've seen, I've shown 3 examples, all of which I've shown quantum key distribution, I've shown teleportation, and I've shown blind quantum computation. All of them use entanglement as its fundamental building block, not the transmission of quantum data. And from this entanglement, they then construct the applications. This is a trend across all quantum networking applications. They build upon this idea that entanglement provides these correlations, this ability to have the same side of the coin, and they can build applications on that, which are secure, which promise to be more secure in some way, and promise to enable new functionalities like the ones I've described. Right, so all of that sounded maybe most likely a bit science fiction, far away. Where is it? Where are we now? Where is it today? I'm happy to say it's ongoing. So that's great. There's many projects across the world aiming at deploying quantum networks, many of them in Europe. Admittedly, all government sponsored for now, but they are happening. Europe has 26 projects within a project called EuroQCI, which stands for European Quantum Communication Infrastructure. Finland also has one. There are several vendors that can sell you, at the moment, all of these networks are actually quantum key distribution networks, I want to emphasize. The only application you can execute at the moment on all of these networks is quantum key distribution. So I've shown 3 examples, but only the first one is doable at the moment. There's several vendors. You can actually go and reach out to some of these vendors and ask them if you can buy that equipment. So example, startups like Lux Quanta or QBird, but there's also like more established vendors like Toshiba selling quantum key distribution equipment. Admittedly, the longest chain that has been constructed is in China, between Shanghai and Beijing, 2,000 kilometers. They also have a satellite to extend the distance even further. The US is missing because the US is skipping quantum key distribution in favor of the next step of the entanglement generation networks. So they're much more in the research phase at the moment and less in the deployment phase. But I've talked about entanglement, but none of these networks that are being deployed actually use entanglement. It's a bit of a trick. Turns out you can implement quantum key distribution without entanglement, but still using many of the same quantum mechanical principles. So that's all still possible. And that's how it's done at the moment. Admittedly, that means they're constrained to quantum key distribution, but they can at least do it. But there are limitations to doing it this way. They basically use single photons, and if you transmit a single photon, a single packet of light on a fiber, it's very easy to lose it. And as I already said, there's a theorem in quantum mechanics called the non-cloning theorem. You cannot copy data. It's just impossible, physically impossible. If you do not know what the data contains, you cannot copy it. Which kind of makes it a bit pointless to even copy it. There are methods to overcome it called basically error correction, but extended to the quantum regime. But they require many, many, many qubits. We will not be able to reach that regime of quantum error correction whilst all of this sounds science fiction, quantum error correction is even beyond that, many decades. So we're not really anybody looking at practical networks, quantum networks, it's nice to be aware of quantum error correction, but that's the next step. So in principle, it sounds like we have a limitation of about 100 to 200 kilometers, because that's how much you can send a photon on a fiber without an amplifier. So for now, when you build these quantum key distribution networks, how do you get this 2,000 kilometer chain? You build trusted repeater nodes, which is where you actually you terminate the quantum connection, your data becomes non-quantum classical, so your key material from your quantum key distribution application is revealed there. So you've got to trust the owner of the site to keep all of that secure. Hence, they're called trusted repeater nodes. But again, turns out there's a solution. The solution is quantum entanglement, which is why there's an ongoing effort to get to that stage. Once we are able to generate quantum entanglement over these distances, we can overcome this trusted this trust in the repeater nodes. Where are we with entanglement? So it has been demonstrated many years ago now, or many years ago. That paper is from 2018 from Delft. And I'm just going to briefly explain how you generate entanglement. In general, you always have to generate these two qubits in one place. You cannot spontaneously create entanglement between two distant locations. And then you take one of these qubits and send it to the other side. Turns out that's not actually the best way to do it. What they actually do is they do this twice at two different locations, and then they send one of those qubits towards a midpoint. The midpoint here is shown with these single photon detectors. So basically they send these packets of light, these single photons, towards this midpoint. The detectors at the midpoint click, and then you've got entanglement between the two sides. And that's basically how you generate entanglement between any two locations over which you can still transmit a single photon. Because the detector clicks and there's two detectors, it actually tells you not only that entanglement has succeeded, it also tells you what state it's in. So you can retry. It actually allows you also for all of these networking mechanisms that are very important to making sure it's robust and actually works. So whilst you cannot copy unknown data, you can keep trying to generate quantum entanglement and then find out from the result what state it's in. Has it been done? Yes. So there's demonstrations outside of the lab. Still experimental, but outside of the lab. There's a demonstration this year between Delft and The Hague. The distance between the two locations was 10 kilometers over about 25 kilometers of fiber. There's also a demonstration in the United States. The two nodes were in the same location, but they used 35 kilometers of deployed fiber. There's different challenges in these two experiments, which I'm not going to go into. My point is, like, these things are being demonstrated now over deployed fiber. Also different locations. What important is when you have two nodes in the same location, very often you take a shortcut that you could not use if the two nodes were in a different location. And in this experiment in Delft, by putting the two nodes physically at different locations, they show they're not even using those shortcuts anymore. There's also a company in the United States called QNext, which is running a continuous testbed under Brooklyn, and I believe they've connected to Manhattan. They're a bit different to the other two demonstrations because they don't have a quantum memory, so therefore they cannot store the resulting entanglement, but they are distributing entangled photons over fiber across the area. And they've been doing so now, I believe, several months now. And what they're trying to demonstrate is they can do this reliably. So I've talked about entanglement between two nodes, but that still requires single photon transmission. So how does this solve the problem of distance? Well, we're still in principle limited to this 100, 200 kilometers. Those examples were even less. Turns out again, if you do generate entanglement between two locations, you can use a mechanism called entanglement swapping. What it is that if you have two entangled pairs and you have a chain of these entangled pairs, you can stitch them together in between. And thus, by stitching them together, you generate an entire end-to-end connection, entanglement connection. You do consume all those intermediate links, but then you generate a longer one. What does it look like in practice? You've got one entangled pair between, let's say, the leftmost node. There's two qubits in the middle, one of them entangled with the left, one of them entangled with the right. And then you perform an operation which is called an entanglement swap, which results in the long-distance entanglement. What you're effectively doing is you're teleporting one of these qubits over each hop up to the end. So if you remember my example of teleportation, you're just teleporting one of these entangled qubits all the way to the end. This has also been demonstrated in the lab. So it's not been demonstrated outside of the lab. So it's still a bit of a step behind. But we know how to do it. Basically, what is important about this is that the challenges are now getting technological rather than fundamental. And as I said, since this is teleportation, you still have to send a 2-bit measurement outcome. So what is the promise of the quantum internet? Where are we heading? In 2018, there was a proposal to split the development of the quantum internet into 6 stages. The stages are on the left, and the examples of applications are on the right. The very bottom trusted repeater stage is the one I've described that we can do today. And in fact, Surf is actually involved in a project as part of the EuroQCI called QCI-NED. So basically, and this entire EuroQCI is at this stage. So it's trials with industry and actually even beyond. So there's many operators across Europe deploying these things. So we're at that stage. There's also other more forward-looking collaborations across Europe. One of them is KIA, which stands for Quantum Internet Alliance. It's a research engineering project, so it's not as much focused on deployment, but developing technology. But it's aiming to build a prototype network of the fourth stage, which is called quantum memory, by 2029. The interesting thing about the memory stage is that at the quantum memory stage, you're going at applications beyond quantum cryptography. There's examples over there. You start looking at blind quantum computing, start looking at you can also enable some consensus protocols that run differently to normal consensus protocols. And with that, I want to conclude by also giving a bit of mention of the Quantum Internet Research Group at the IRTF. So as I said at the beginning of the talk, I co-chair this group. In fact, actually on Friday, we're having a meeting at the currently ongoing IETF meeting. You can still register and join online. It's from 9:30 to 11:30 of Dublin time. It does say first informational RFC finishing review. 2 informational RFCs have already been published, not just are undergoing review. So if you're interested in more, here's the introduction/abstract from one of them, which of RFC 9340, which aims to introduce the subject in more depth to a networking audience. And with that, I thank you for your attention.
So again, we are a bit late, so I'll limit the number of questions to just the ones I come up with. So at this point, all the plans are for a parallel infrastructure with the internet.
Yes, so actually I probably should have mentioned that more. So the quantum internet is not meant to, it's meant to add functionality to the existing internet. Actually, out of all the examples I've given, none of them even promise increased bandwidths, for example. So the plan is that your regular infrastructure will stay the same. Quantum networks will just give you all of that extra functionality, which you can then add on top to all the applications.
But can you put these quantum connections through the same wavelength division multiplexers as the internet, or do you really need dark fiber?
Oh, so there are yes, you can put it on the same fibers. The cost is that you're losing distance because the noise from the classical data is quite overwhelming for the single photons. But it is possible. You just lose distance and performance.
Thank you. Quick question. What kind of data rates are we looking at here?
So for quantum key distribution, they're looking at kilo to megabits of like secret key material, and that's, I think, after post-processing, so that's not the rate of the photon transmission, but that's the rate of the photon transmission, including all of the ones you have to throw out to check if there's an eavesdropper. But that's quantum key distribution. For entanglement generation, depending on the distance, in a single room, you're looking at 50 hertz. Across a distance, you're looking at like 1 every 2 minutes or something. So if you're doing entanglement, it's very, very low rates at the moment.
One more question. So the first production uses would be militaries and financial institutions. Is this correct?
Actually, yes and no. In principle, I'd say everything. So also government communication. The first EuroQCI is mostly about government communication. But I kind of don't really want to sound scary, but the quantum computing, supposedly a lot of experts say quantum computers are going to be here by mid-2030s. And that means all infrastructure is in danger at that point. So if not quantum key distribution, there's also an alternative called post-quantum cryptography, but it's already time effectively to start looking at ways to start using these early stage applications like quantum key distribution. But yes, the people who would be using quantum key distribution are governments, military, finance, anybody who needs that extra layer of security, medical data, and so on.
These two technologies, post-quantum crypto and PKD, also supplement each other?
Yes, and basically they have different trade-offs. One is easier to deploy, but is not guaranteed to be safe against all future technologies. quantum key distribution promises to be secure against all future technologies, but requires infrastructure, unlike post-quantum cryptography. So it's a trade-off. It depends how long your data needs to stay secure for, effectively.
Okay, thank you.